Okay, let's get this done. So can I move forward to the next joint?
Which one?
D.
Yeah.
What is the first step that you do whenever you resolve a joint? Draw the free body diagram. These are the tricks. If you draw the diagram, you just can't get it wrong. No, you really can't get it wrong. It's very hard to get the structures wrong. Where did I drop the black thing?
It fell forward.
Where it fell on the floor? Thanks, Hans. Okay. So what does the free body diagram of joint D look like? That's D. There's one member going down, there's one going like this. That's F, that's E, that's C, that's B. How much is the force? Okay, what are the forces that are applying at joint D? We'll start with Thomas. We'll just go one by one. Thomas, what's the first force in BD?
45.
45. And what direction is it acting at joint D? Towards it, right. Casey, what force is in DC? 25. And what direction is it acting in? Huh? Towards D, okay. Berta, DE.
Unknown.
Unknown, okay. Andy, DF. Unknown. It's always useful to lay down the facts you know on paper so that you know exactly what to focus on. The key is to unclutter your mind whenever you're doing calculations or anything analytical. You put as much on paper so you can basically free up your memory so that you can actually deal with stuff that you don't know. So what's the first resolution that we do when we resolve at joint D? We resolve for vertical forces at D. So what are the vertical forces at D?
25.
Well, let's start with the forces from one end. Let's see if... Who's this? Ryan, you need to staple that, man.
Oh, jeez. Yeah.
Okay, BD. Does it have a vertical component? No, so we don't even need to consider it, right? Does DC have a vertical component?
Yes.
Absolutely, it's entirely vertical. So F, DC. How about DE? Does DE have a vertical component?
Yes.
And what's the vertical component of DE? FDE, right? Ben, the vertical component of DE is FDE, correct? Yeah.
Sine 45.
Why sine?
That's the vertical component.
Of an angular force, right? Because it's an angular force. Any angular force has a vertical and horizontal component. This is not an angular force. It's a purely vertical force. That's why the entire force applies, right? How about dF? Does dF have a horizontal vertical component? It doesn't. So the sum of the vertical components of the force at any joint equals how much? 0. Okay. Equals 0. Or FDC is how much? 25 plus FDE times 0.707 equals 0. Or FDE equals minus 25 divided by 0. Sorry, 0.7. Okay? Right?
Right.
How much is 25 divided by 0.707? 45? How much?
35.
35.36. Okay. 35.36. Now, what direction will this force act in? Remember, there's a negative sign here, right? Because it's minus 25. So it's negative 35.36. Which means it's acting in whatever is the opposite direction of 25. What direction was 25 acting in? Huh? F.
Yes, we're right.
Yeah, okay, sorry. You're right.
I was like, oh my god.
So it's acting in this direction, right? Okay? So, going like that, and this. And the quantum is 35. Okay, now that's done. What do we do at joint D after we've resolved for vertical forces? Horizontal. This is why you guys need to come in for that extra class, because I am burning up very valuable like chapter 16 time in dealing with
Because you
stresses.
waste our extra classes.
In what?
We already had an extra class.
I know, but you guys need to catch up more. You need to then work at home.
Teach us better.
Shut up. You can find somebody else to teach you. I'm happily step out. I'm serious. Yeah, I totally need.
It's been so long.
Okay. Hey guys, what are the horizontal forces? Who's already calculated it?
I'm not sure if it's correct.
Okay, give me the equation.
So I did 45.
Okay, 45, which is, so don't, the trick is don't say 45. First,
Okay,
list the,
I did
yeah,
FBD.
FBD.
And then I did minus.
So DC doesn't count, right?
Right.
Does DE count?
Yes.
Plus FDE times cos 45.
Okay, so that's, I did minus because that's what we did last time. Why is this one plus?
All I'm
Because they're in
saying,
the same direction.
sum of all the, well, you don't know the direction yet. Just list it down for the time being. I'm not even,
No, listen to my question.
you're jumping one step ahead.
No,
Just-
I'm on this step. Listen to my question.
You're asking me about the sign. I haven't even reached the sign yet.
Of FDE,
Yeah, I haven't even reached the sign yet.
you put plus.
Sum of
Can you listen
yeah,
to
will
my
you let me
question?
finish?
You're not listening to my question. So how are you going to finish when you haven't listened to my question?
Okay, tell me your question.
Okay, so in the previous one, we did 20 minus the 63.6.
Right.
So I'm wondering why this time it's not minus again. Because you put plus.
Well, right now, I haven't even input the actual magnitude of the force. I'm just listing what are all the horizontal forces at that joint.
So when you put in the number?
When I put the numbers, I will put the direction. Okay?
Okay.
Remember, I keep telling you guys, put that extra step. If you have that extra step, you just can't go wrong. Okay? So FBD, FDE, are there any other horizontal members? Sam? Plus FDF equals 0. Just remember, the theory says the sum of all the forces at any joint, whether it be vertical or it be horizontal, always equals 0. That theory, and in order for this to equate 0, some of these forces have to be negative, which is the answer to your question, Berta, right? Because if they were all positive, the sum would be 0, which is why automatically some of them have to be negative, right? So, how much is that BD? 45. How about DE? DE is 35.3, right? 36, okay. So plus, it's in the same direction, right? Plus 35.36 times 0.707. Okay. I don't know the direction of DF. I can pretty much guess it's going to be in the other direction, right? Because there are two forces. One force is going like this, the other force is going like this, right? So by looking at the diagram, I know it has to go in the other direction, but I don't need to put it there for the diagram. So plus FDF equals 0, which means I can calculate FDF. How much is FDF? How much is 35.7? 25? Ryan,
Yes.
your eyes look glazed.
He's sick. He's asleep.
I am sick. I had the calculation though.
Okay, so how much is FDF?
Yeah, and I believe it is. Mine, yes, mine's incorrect. I got a negative 25, but it's 70.
You didn't add any other 45.
Yeah,
That's it.
yeah. So
Is FDF 70 then?
looks great.
Has anybody reached this stage?
Yeah, that's what I got.
I did negative, so I got 20.
It wouldn't be 7 because of
Wait, what's negative?
Smaller.
Well, because I did what we did with the last one, so I made the 35.36 plus I made that negative. That's where I was confused.
the value of DE
So-
can be less
But
than
you're clear.
Yeah. So how
Right.
would it possibly be 70?
Because the whole trick is to draw that.
Wait,
Basically, you draw this.
wait. Isn't F D E, isn't that negative?
See where you did
Negative 45?
DE?
No, F D E. I got negative 45.
Yeah,
Is that wrong?
I just did.
Wait, isn't force, okay, isn't force DE 35?
What?
Is force DE 35? F,
Yes. Yeah.
so the horizontal component of 35.36 is how much? 35.36 times 0.707, which would be 25.
Yeah. No, we just didn't add in the other 45 from BD.
Yeah, we didn't add in FBD.
That's why we
But
came up with
is
25.
FBD negative or positive?
I'm taking it as positive.
Because I have it down in negative. I don't know why.
Wait, is FD in compression or is it in tension? compression, right? In which case, this arrow is going in that direction, right?
Positive.
Do you have that sign, Ben? When you calculated BD, did you get that sign?
No.
What sign, what direction was your sign going in?
I didn't have a sign.
Okay, sign is really important because without a sign,
Oh, I knew
you
it.
won't be able to calculate it.
I just didn't work the sign.
Okay. So just remember, that's why it's very important you keep putting those direction of those arrows. Because a force is defined as magnitude and direction. If you don't have a direction, you don't really have a force.
So it is 7.
It would be 70, right? Because BD is going from left to right. DE is going from left to right. Therefore, DF has to counteract it by going in that direction. It really is a 10-minute quiz problem. You know why? Matt and I solved it in 15 minutes flat because this was the problem we did at the end of today's class. So that's 70.
Making us all feel stupid.
I didn't say that.
Doesn't matter.
That wasn't your point to telling us that it took you 15 minutes?
No, it's different.
Okay.
Matt has the advantage of, remember, getting one-to-one instruction. You know, it's very different. So, you know, if you divide the amount of time that Matt gets, that's like each one of you getting a 3-hour class. Okay, so DF is 70, right? Now, which joint do you want to do? Because we've already gotten all these 3 numbers. So that's 70.
We just need FE and then we just flip it and then it's symmetrical.
FE? Okay, let's do FE. Let's get it done. Has anybody solved solved E?
We tried to.
Did a solid.
Good. I'm glad you tried. That's the first step towards getting it right. So, again, what's the first thing you do? You draw the free body diagram. We've got a force of 15. That's E.
Wow.
C, D, F, H, G. Okay. What are the forces that we know that are playing here?
CE is 45.
CE is 45. And what direction is it going in?
That way.
Yeah, because remember, I'm just interested in this section, right? How about DE?
35.36.
35.36. How about FE? Unknown. How about HE?
Wouldn't it be exactly the same as the side we just did?
Well, you're probably right. You're definitely
But
right.
it's unknown. But it's unknown.
But for the time being, it's unknown.
Oh yeah, we did.
How about EG?
Unknown.
Unknown. Great. So resolving for vertical forces at E, right?
Yeah.
Casey, why don't you tell us what are the vertical forces at E?
Oh, we also have the force of 50 going down on the. Oh, you're.
Yeah, I've already got that. Casey, what are the vertical forces at E?
Would it be 50?
Okay, 50.
And 35.
So I'm going to do it like, you know, in an even simpler way so that we list all the forces. Does CE have a vertical component? Nope. Does DE have a vertical component? Yes. FDE sine theta. Does FE have a vertical component? Possibly.
Minus
F,
Is it?
F, E. Does HE have a vertical component?
Yeah.
Yes? EH. F, EH, sine 45, right? Any other vertical forces? Does EG have a vertical component? No. So we got this doesn't apply, this applies, and this applies. Right? And the sum of all these vertical forces equals 0.
So technically, isn't it impossible to solve until you solve the other side?
Huh?
Isn't it impossible to solve E until you solve the opposite side?
That's where the trick of this problem lies. Now we've got, normally the way we do is we always have one unknown, we get an equation, we solve it. But suddenly out here, we have two unknowns, right? Because this doesn't count. FE and FEH sine theta. So technically Noah would be right, it's unsolvable. However, I can tell you it's solvable. And why would it be solvable?
Because the side is exactly the same. So,
How much is the force in FEF and FEF? How much is the force? How much is this force? That's the key to solving this problem. How much is this?
50.
50. Ben says 50.
0.
Berta says 0. Sam, who? Okay, let me give you some numbers. How many of you go for 50? Let's have a show of hands.
50?
50. Ben, Ryan, Noah, Neil.
My favorite part is not to
How many of you go for 0?
I don't have a clue, so I can't even.
You don't have a clue? Okay, why don't you come forward and let's give you that clue.
I really just need to watch you do it because I'm a visual learner.
Okay.
That's what we're in there.
Do you remember? No, do you guys remember when I taught you that a vertical force cannot become a horizontal force? Remember, a vertical force can never become a horizontal force.
all right, elaborate.
Hmm?
Elaborate. Do that.
You know, I've been saying that for the past 6 classes. A purely vertical force
No, I know that. I know.
will never turn into a horizontal force. Just like this, because at A there was a force of 45, it could not go into AC, right? Because AC is horizontal. Similarly, so as you're solving this, that's why it's important to keep making that diagram. Like you keep filling in this diagram. You realize that if force FE were to carry a force, it would have to go to joint F. Supposing there is a force on this. As you said, supposing there were 50 pounds on that, right? It would have to go to joint F to be transferred somewhere. But from once it reaches joint F, it can't go anywhere because it's a purely vertical force. Because this is a horizontal member. A vertical member, when it reaches a horizontal member, it cannot transmit a force. In other words, this is 0. Because supposing you had put a force on this, once you resolve that joint F, you could not resolve joint F because joint F has a purely horizontal force, right? You just can't resolve that joint. Does that make sense, Thomas? Right? Because supposing I had drawn F out here, and this were coming from E, and I said this is 50, how would you resolve F? You just can't resolve F.
What?
Huh?
I don't get it.
I understand. It's like question 4. Whatever this is.
Right. It's like question 4. Guys, remember question 4, which was like this? There was a vertical member, and I was trying to ask you that how much, if this is 200, how much is the force in that member? And the answer in this was it was actually 0 because it would go on these to be 100 and 100, which means this would be 141 and 141. Right?
So to make the problem, no, that didn't work actually. Never mind. Answer my question.
So where's the 50 coming from?
In other words, what is pulling it back up is your question.
Right.
ED.
These guys are pulling it back up
So that other.
because the vertical component of 35.3 is how much? 25.
Oh.
And how much is the vertical component of EH? Because it's a symmetrical truss, right? It's 25. So basically, FE doesn't even come. So 50 plus FDE plus FEH equals 0.
I think it was the opposite direction. It was throwing me off. If it looked
Anyway, yeah.
if it looked exactly the same as that, I would have understood it.
It's definitely 50.
So just remember this.
Why we doing the quiz question?
Yeah. They're not even new. Yes.
Supposing I were to give you a truss like this to solve,
Don't, but keep going.
if I gave you that truss to solve, okay? You can be pretty sure that these blue members have absolutely no force on them.
So they're there for.
Stability.
Exactly, they're there for stability, as I said in the last class. What they do is, supposing the member's being compressed, right? It's a really big member, and it's really long, and it's being compressed. Just in case anybody even pushes it out slightly, it'll just compress entirely. It's like taking one of those steel scales and trying to compress it. It won't compress as long as it's perfectly rigid. But even if you push it out slightly, it'll immediately compress. So these members are there to keep the truss rigid. In other words, it's to reduce the effective length of a compressive member. You will study about effective length of columns in the next semester. Ryan, your question.
There would be a force on it if it came down like right in the center of that truss you drew. Like right
Here,
No, on the one you just drew. Right on the center of that, on the top.
this one.
Yeah, if it came down on that member, there would be a force on it.
Supposing there is a,
No, if it came down on top, so it didn't compression. You know what I mean?
come here and draw.
Here?
Yeah.
No, there wouldn't be anything.
He's absolutely right. There would be a force. Think about it.
That would be
If you're putting a force of say 50 out here, okay, and it's going down like that, this is great because now we're going into truss without the math. Okay, this is just conceptual. So supposing you have a force of 50 going like this, it's a great question from Ryan.
well, that's what I thought the last one was. That's why I messed it up.
Because it would come down.
It would come down like this, then it would go back up like that. Right?
There'd still be no vertical reaction on that.
Well, it would be.
On that,
There would be.
that number.
Yeah, no, it would be like this and
Yeah,
like
see
this.
what it-
So how is that different than what we're?
The reason is, Ben, remember this is connected at the other end to angular members, which means as it transfers the force from this point to that point, at the other end, there are vertical members that can take the force back. Just stay with me for 1 second. Let me get my red
That's what.
marker.
It's just doesn't that look exactly?
Okay. See, Ben, remember these two members have vertical components. These guys, they're angular forces,
Right.
which means these two are basically pushing up in that direction.
Right.
So when 50 comes down on this, at this end, it's pushing it back up, which means at the other end, it's pushing back down. This guy is getting pushed down like that. But then these two guys pull it back up because I've got angle forces out here. It's pulling it back up. It's like basically you're standing on a column. Imagine you're standing on this column that's being held by two strings. Because that's how it's working. That's a column and it's being pulled up by two strings. Now, if you were standing on a column like this, if you were standing on a column and there were strings here, none of that force could be taken by those strings because those strings are horizontal. But if you were standing on a column with strings at an angle, the strings will pull you back up. Okay, you're still unclear. We will resolve this. So Ben, your question is, in this case,
Why is that different than that?
okay,
Because this force is being pulled.
because it's basically if you flip it over, it will work the way it's working this way. It's just
because the 15 arrow on top on that one. And on the bottom.
Yeah.
Oh,
Yeah.
okay. That's all I need.
but you understand why that's happening, right?
I get that, yeah.
Because here,
If they're touching,
E
it
is
doesn't
being
work.
pulled
If they're not
down.
touching, it works. That makes sense?
listen, E is being pulled down, right? So if it were to pull down F with it, supposing you were to transfer that force along EF and you were to pull F down, that force has nowhere to go once it reaches F. Because if F has only horizontal members touching it, right? But here, as soon as it hits,
Arrows on top. I get it.
you get it, right? Because here, as soon as it touches this point, it will not go sideways. It can't go sideways, right? So it will go down, and then it's going to get pulled back up. And then it's going to get pulled back down like this. And then it's going to get resisted like that. And these members are just, they're not taking any load. We clear? Okay, exactly 5-minute break before we flip to chapter 16.
I've got a question.
Ask the question.
Upstairs.
So when we're looking at this one that we're doing. So. Like how come this wouldn't be 0 too? 'Cause that's like,
Remember, it's got angular members on both sides. Every
what was
angular,
in these?
yeah, but it has a perpendicular member like this. It can't go anywhere else.
Oh, just because that one. Oh,
So I'll draw it for you then. Say if we were to just redraw that, okay?
Yeah.
So you've got a member like that, you've got a member like this, you've got a member like this.
Yep.
So if this has a force that's going like this, that means these would basically need to push in that direction, that would need to push in that direction.
Yep.
So in other words, it's going to go like this, it's going to go like this. Okay? Now, in this case, you've got a force like that, you've got a guy like that, and you've got a guy like this. Okay? So supposing this is getting pulled down in this direction, your first question is why can't this get pulled up? Right? But it can't get pulled up because if it goes in that direction, it has no way of going here or there.
Okay.
Right?
Yep.
Makes sense. Because this is a horizontal member. Which is why it is forced to go up like that and go up like that. Because it can't do that. Because supposing it did go here, but where would it go? A vertical force cannot become a horizontal force, right?
right, yeah.
So because there is a horizontal member here, it just can't go.
Okay.
Okay? So for practical purposes, this element might as well not exist. This is like, this truss is basically like this. That member just doesn't need to exist. Make sense? Keep doing this problem again and again. Like take this problem, change something else, solve it. Keep solving it, they will get adept and fast at it. It's also a test of speed. How much did you get it? The problem that we did. Bit more clearer this time? Good.
So does it end up being the same for the other side?
Wow. got a very nice case. Really well integrated into the design. Hey.
Zach still hasn't gotten this.
Okay. Cool. Wow.
What?
It is really nice.
So wait,
Yeah, I interrupted.
listen, trust us,
Cool, wait.
listen.
Yeah, this is the future of our food. This is not at all. Yeah, I can totally live with that.
Yeah.
Yeah, it's great.
They've only had pretty much the same thing the whole fucking time rifle, just slightly modified each time.
Nice. Great. Okay, what's the question?
So that means since this is like you said an even one, then one gives you the same answers for this side.
Absolutely. You do half the cross. If it's a symmetrical cross, you just solve half of it, and the rest of it is there.
So like this one is gonna be 45 going
Exactly.
the same way. Or
Yeah,
the
exactly the same.
the same.
I
Remember, no
I
force for
did
please
the-
don't draw arrows on that.
Oh, okay.
Yeah, don't do that ever. Because you get confused. No
I had
arrows.
to do
When there's
research
no
at
force,
work
there's
the
no
other
arrows.
And so I literally, I went
It's
into
either
him.
all
I
45.
was like, so my research,
Because
in my
see, there
research
is
I
no-
found,
If
and I
this
realized
had a
how
force
very
in
nice sounded, so I literally went,
Right? It has to go to the ground somehow. But it can't go to the ground because the ground is purely vertical.
Okay.
Right? You know, horizontal force cannot become a vertical. You see what I mean? Okay.
What is it doing? Is it
like
like
that?
Trying to
Mine takes
like
out.
cross around.
one more big one?
I want to do chapter 16. So what I would start on chapter 16. What I would suggest is I'm happy to do another one on Thursday if you wish.
Nope,
Oh, wow.
no one has time for that,
I'm
we're in
getting-
studio.
You're getting, do you realize how expensive a tutor is if you were to really get a tutor for this thing?
Do you realize how important studio is?
Do you realize you'll never have a teacher who willingly sacrifices their time to take extra classes?
Were we assigned to chapter 16?
Huh?
Were we assigned to
No.
chapter 16?
Because I want to introduce some concept before you study chapter 16. There are some concepts that you need to study. Okay, it's time to start. So let's go.
Does that not look like,
Those look- yeah. Looks like your thing.
Hey, question.
Yeah.
My studio project is now like
Earth?
hills,
Uh-huh.
and I don't know how to make that in Rhino.
Rolling hills.
Do you know how to make that in Rhino?
What are you trying to make the hills?
Yeah.
Just draw a topo,
I think someone has it.
elevate them, and loft it.
I think my cousin.
You have your topo, right? You've got your topographic lines.
Well, but there's building underneath the, so it's not like a full hill, it's like,
Carving and out.
yeah, it's like a little strip.
Okay, so all you need to do is draw the topographic lines in plan.
So she has to make up her own.
No, but you don't need the intermediate topography. You just need like major,
Top,
yeah,
middle.
like, you know, top,
Yeah,
middle,
like-
right. And then create a surface. And then, you know, you can just create topographic lines in Rhino on that. Remember I showed you that command? How you can get those into, we would draw topography and then it would do the topo lines for us. It's there, it was done in the second class.
Wait, what did you say?
Remember we drew this to a terrain in Rhino and then we drew topo lines in it.
I remember doing the thing, but not.
Yeah, it would be like cutting basically lots of slices through it. You could do it horizontally, you could do it vertically in any direction you wanted. So that's what you need, you know, for your drawing purposes. Just just draw simple lines like I'd say every 30 feet or every 40 feet. And then just approximate it.
Oh, shit.
If you get your computer on Thursday, I'll show you.
I will not be sassy the rest of this class. Bear with me, it will be difficult. I might have some lapses.
Okay, I'm going to start with chapter 16 because these kids aren't, class has begun.
Okay. Just 5 minutes.
It's anyway okay because the whole class is getting streamed, so you can always review your notes later on.
That's what I have to do. I need a nap.
Okay. So chapter 16 is really simple.
I can't believe it's 6 o'clock.
I can't
My
believe
life's
I'm reading
over.
this. I'm reading this.
Oh yeah, you're gonna
class.
have to have heavy makeup class,
Yeah, where the hell is he? What's here?
He's sick.
No, you were
So
here earlier
Ryan.
today.
I know he spoke to me and we agreed that he should go home because otherwise all of you guys would be falling sick.
Is that how
I've been taking emergency twice a day for the past
Then
month.
can you make Ryan leave? Because he's also sick and
Is that
crying.
like bronchitis?
As long as it's not contagious, it's okay.
Bronchitis is contagious.
Bronchitis is not contagious.
Huh?
Not contagious.
Yes, it is.
Not by
First
air.
24 hours.
Not through air.
So you just-
But he coughs on people and spits on people.
That's
so.
true.
That's air.
Well,
Right.
he should not cough on people and spit on people.
Right?
Well, he coughs on people even when he's not sick.
It's true. It's disgusting. He's a fucking savage. I truly despise him.
What about language? Okay, so that's a beam.
Wait, are we working on one in particular?
We're looking at chapter 16.
Right, but is there one in particular that you're looking at?
I'm just looking at the beginnings of chapter 16.
So how I get that in a moment.
Okay, so that's a beam. When a beam is subject to loading, what happens?
Sagging.
Bends. That is sagging.
The man is that.
So in other words,
I wonder why they changed it then. This one.
Because you have to know what direction it's bending.
if a beam goes up like that, hogging.
We did say sagging.
And those two things are
That's.
Now,
Are we gonna do one?
Oh, really?
I've never done one.
No. I feel like I failed very fast.
Oh, yeah, I have really worked on my mom now.
I'll show you the video.
okay, so what's an example when a beam might show hogging? Sagging is pretty clear. You've got you've got a guy standing on this thing, it'll sag.
the columns don't end.
Right, when columns don't end, so if you were to move these supports a little bit inwards, how would the beam deform? It would deform like that and then bend like that, right?
What's that like? I'm talking about like how the columns fail.
If, yeah,
They go
and then
in,
they
they're
start
attached,
pushing.
they go in, they push up.
Now, for example, say I had an example where I took this guy out and I loaded him up on both ends.
That's what I was thinking.
And there's absolutely no load here. In other words, you've got this beam that's being pushed down at both ends. What happens to the center span of the beam? it pushes up. So basically in that case, the beam goes up like that and it goes down like that.
That's
Right?
what I need for it.
So in this case, it has sagging out here, hogging in the middle, and sagging out here. Okay? Right? Now in this beam, supposing I were to now place a dude in the middle, I can effectively counter the hogging so that my beam's kind of like this. Right? Which makes for very efficient design because I'm putting steel in my structure so I can deal with the sagging, right? But if I design my building in such a way that there's hogging in the middle, I can just put load on it to counteract the hogging, and my structure is extremely efficient. So what's an example of a structure like that? You would typically find it, supposing you're going to look at a building. Say these are my columns. Okay? And a section through the building is going to be like this. So if I put a load on the building out here, it's going to sag like that, right? Yeah? In fact, it's pulling the columns towards each other. However, now if I were to do a different thing, and say I take these columns and I move them a little in. Okay? So what I've done is I've put columns here. There's no column here anymore. What's happening? There's going to be sagging out here, hogging out there, and sagging there. Right? In other words, if I've got a support here at both ends, that's how the thing will bend under load. Right? Because once you put, say you put the walls and all that stuff, and you put your masonry and you start loading this part of the wall up, and you start putting that part of the wall up, it's basically pushing down on the floor slab, on the beam, which means it'll pop the middle portion up. Which means now you can go in and start putting your refrigerators and washing machines and furniture, and the floor would be absolutely flat. So earlier, in the earlier case, if I had to put a lot of load on the floor, I had to put extra steel in my building, or extra, deepen, make the beams thicker. But by cleverly moving the columns in, what I've managed to do is I've managed to use the design of the structure to counteract the force. Okay? Which is why it's important to know where sagging is happening, where hogging is happening. It also has lots of advantages. You don't need to dig that much for a foundation because your columns are closer and aspects like that. Usually in a building, it's rare that you push all the columns on the outside. You only do that to get rigidity to get lateral stiffness. You normally pull the columns in because the cantilever moment counteracts the beam moment, which is why today we're going to study about moments and shear force diagrams, okay? Bending moment diagrams and shear force diagrams. Okay, so we're looking at figure 16.2, figure 16.3. Now, we talked about bending and shear. Do you remember when we talked about bending and shear? Let's see how much attention Andy paid. Do you know when we talked about bending and shear?
Yeah.
When was that? Good answer. You really did pay attention. It was the second class because it was chapter 3. Okay. What is shear? Let's go back to our beam. We all know what bending is, right? Bending is when it sags in the middle. Fair enough? Sagging also is a form of bending. I mean, hogging is a form of bending, right? Because it's just bending in the other direction. It's bending all the same. So if I had my beam like this, I'd say it was simply supported thing. There are two columns on either side. And I put, say an elephant. Then I put an elephant in the middle of my beam. What would you expect to happen? You would expect the beam to sag. Right? What if I wanted shear to happen? What would I need to do? Since Andy remembers the second class, Andy can define shear for us and then tell us, when does shear happen? So where would you need to put the elephant for shear to happen? Let me see what you dressed as. When do you come here and show me where shear happens?
You're skinny enough to be cool.
Where do you need to move the elephant to have shear?
On what?
On this beam.
Yeah.
Where does this elephant need to go for shear to happen?
Well, either there or there.
Why?
Because it would cause shear along that point.
Okay. Andy's absolutely right. And more importantly, the gorilla is being captured as part of the video of the class.
Oh, yes.
You didn't figure out that's why I made you come up front.
Oh. I mean, I just thought I was smart or something.
He likes his painters in the.
No one thinks you're smart.
Okay.
I don't remember the next time they asked for a rhino.
Let's draw the reactions for this. So we've got the reactions are that, right? You've got a beam like this, and you've got reactions at either end, right? If I have the elephant in the middle, I've got a force in the center. But if my elephant moves to this end, right next to my reaction, like just immediately to the, say, the left of my reaction. Remember that slicing action that was all about shear? You have insane amount of shear happening here. Can you think of an example like this in your houses where shear might happen?
Yeah.
Look up. Do you see shear happening anywhere out here? See that beam?
Right there.
Right. Whenever beams meet columns, there's a lot of shear happening out there, which is why you put straps around. If you go down to your basement and you look at the joists and the beams, you realize there are always these steel straps that you tie wherever a beam meets a column. Because what's happening is those nails, it'll just try to shear that nail off. It's not through bending that the column will fail. So that's shear. So shear in a typical beam and column system is maximum where the columns are. Okay? How much is the bending? If I were to put this elephant out here, how much is my bending happening out here if it's at that edge, closest to the column? What is bending? It's a moment, right? What's the formula for moment?
You're saying that shear doesn't happen?
There's maximum shear there, yeah.
Yeah, that's what I said, girlfriend. Or like.
Oh yeah, absolutely.
Okay, good. I just want to make sure I was wrong.
Oh, I thought you meant a hinge.
No.
I heard door, I didn't hear door frame.
That's door.
Okay,
I didn't hear wrong.
so
Force times distance.
force times distance. How much is the moment out here? it doesn't matter how heavy the elephant is, right? Because what matters is how much distance is the elephant from my column. The closer the elephant is to this guy, the less the moment on that end. However, there's greater moment at the other end, right? Because at the other end, the elephant is at quite a distance from that column. However, my shear force is maximum the closer I'm to my point of support, right? So the further my elephant keeps going, the further my elephant goes, the less the shear becomes. Because shear requires the fibers to basically slice against each other. And as I move further away, there are that many more fibers slicing against each other, means that much friction. So there's less shear. Okay? Now, typically when you design beams, you design for bending. Why is that? So the depth of the beam, like say, let's take the beams that we've got up above. They're basically dealing with two types of forces. They're dealing with bending, which is they have a tendency to bend down like this, and they're dealing with a tendency to shear. And the thickness of the beam accounts for both the forces. So the depth of the beam will say, well, if I am, say, this is about 12 inches deep. If I'm 12 inches deep, there's that much of shear force that I can take. And if I'm 12 inches deep, there's that much of bending force that I can take. Okay? Now, typically with beams, with all regular beams, the amount of depth that you need for this beam to resist the shear force that typically is applied on this would mean you can get away with a beam that's like 6 inches deep. You don't need that much shear depth for shear. But 6 inches deep beam will fail in bending. It'll just bend in the middle and crack. So you end up giving the beam a lot more depth so that it can counteract the bending, so that you don't see it deflect. Remember, deflection is just a vertical movement in the beam. The beam is too sound. It's just, your floor would have a dip in the middle. But you don't want that dip, so the beam stays, 12 inches deep. There is one case where the shear force becomes far more important than bending. What case is that?
What's the question?
Yeah, wait, say it again.
So I just made the case that typically with beams, the shear force is not as important as the bending. We design beams for bending because this beam needs to be 12 inches deep to hold up that elephant in the center of the room. And the beam just needs to be 6 inches deep to deal with the shear of the elephant at the edge. So you by default go with the larger dimension, right? So that you can deal with the bending. So the beam is extra strong in shear. Okay? Sure you're paying attention. Good. Now, there is a case where the beam, in a certain type of beam, shear becomes far more important than the bending. What type of beam could that be? Think about the formula of bending, in other words, moment. What is moment? Force times distance.
Would be a cantilever?
Typically, when the distance becomes very small, you don't have that much moment. Because, when your beam is, say, like 3 feet wide, like, say, the span is 3 feet, and, supposing I were to put a heavy block of, say, steel or a safe, okay, it's a really heavy thing, say that weighs like a couple of 1,000 pounds. So it doesn't matter if it's a couple of 1,000 pounds. The fact is my moment isn't a lot because, moment is force times distance. If it's only 2 feet wide, the moment at the center is 2,000 pounds times 1. It's just 2,000 pound feet. Now, if I were to take, say, a 500-pound weight and put it 4 feet or like, say, 6 feet away, that's causing a far greater moment on the beam. So that beam can only be, say, 8 inches. However, When objects come very close to each other, the shear becomes exponentially high, right? Because shear is all about the number of fibers that are there, which are providing friction. And you don't have a lot of fibers because it's just, very small. So just remember, usually with beams, you always design them for bending unless they are short beams. There is a special class of beams. Hey, remember, this is an ARE question.
And then you just make them.
You design them for shear. Do not design them for bending.
They just become thicker.
They become thicker. Basically, you calculate the shear and you design the beam for shear. So when you design a beam, it's really simple. You're calculating the bending moment. What is the maximum moment it can take? What is the maximum shear force that's being applied on it, right? And then you look up the tables and you figure out for this kind of this size of an I-beam or this size of a, say, Douglas fir beam or whatever type of beam you're using, say teak, or any type of beam that you're using. You look up how much is the load it can take. Calculate shear, calculate bending, and you can size the beam. That's what pretty much every contractor is doing. When you're like doing, say, roofing joists, that's what you're doing. You're calculating how much bending, how much moment a truss can take, how much shear a truss can take. And you say, look, this is the snow load in Maine. So based on that, that's the amount that I need to design. And you put a factor of safety. Okay, let's move forward. So, let's calculate some shear. We're going to look at example 16.1. It's the first example. Oh, sorry. Yeah, 16.1. This one.
Oh.
No, the example 16.1.
Oh my god.
Did you want us to actually
Stop it. No reason that much detail. Some of my thing was like breaking brain out of
Really?
That's what I was thinking.
Okay. I'll teach you guys to calculate shear force in like 2 minutes, and you just can't get it wrong after this. So let's draw this diagram, okay? It's 2, 3, 4, 6. We've got a force of 30 kilonewtons on here.
30 or 50?
It's 30.
What is it?
Well, since you were talking, I couldn't hear him.
Oh, stop. But it's sitting down, it's sitting down, see, I can see. It's another point.
Okay. So we're going to basically graphically plot out the shear as a graph. How much are my reactions?
Yeah. Super.
What's the units on the 10?
Kilonewton.
Giganewtons?
Yeah. Now, you know why I've been stressing so much on the whole idea of calculating reactions, because you can't do anything unless you calculate reactions. So how much are my reactions?
Wait, did you change it?
Yes.
What did I change?
You just put the X at A.
Anytime
We haven't
range
reached there.
from 1 and
No, we don't.
2.
Right, well, that's because.
It's fine. So this is 25. And how much is this?
Oh, mother, 15.
15. Okay. Okay. Now what is shear? Define shear. It's basically the slicing force, right? And for shear to happen, what are the two components I need? One force going up like this and another force going down like this. Right? One force going up, one force going down. Okay? Now, how much is my force at A? No, forget A. Screw it. Let's go. How much is the force at this point? How much is the force at this point? Huh?
Where?
On my extreme left. 25. Okay, so that's 25. Okay? I'm going to move to the right. How much is my force at this point? I'm looking at a beam, right? I'm trying to calculate the shear in a beam. It's a beam that's 6 meters in length, and it's got two forces of 30 kilonewtons and 10 kilonewtons that are acting at 2 point roots. So shear is nothing but force, right? Shear doesn't, what are the units of shear? Pounds. So to understand the shear in a force, shear in a beam, all I need to do is calculate the force in the beam. Fair enough? So how much is the force at my reaction? 25? Yeah? Now if I were to go, say, 1 meter to the left, to the right of that beam, and I reach here, how much is the force acting on that guy? Still 25. Because no other force has started acting. So I keep going. It's still 25 out here. I'm just drawing a graph.
Oh.
Yeah.
I was wondering what that was.
Okay. So I'm going to keep going to this, still 25, 25, 25. Then I reach this point. What happens at that point? That force of 25, which has been created by my reaction, that's basically pushing it up, right? Suddenly gets impacted by a force of 30 kilonewtons. What direction is 30 kilonewtons going in? Down. So it's going to go all the way down by 30. So if this is my 0, that's 25, right? That's 20, that's 10. This is basically 5. So it's 25 minus 30, it goes down. Okay?
Okay. So, right now, no idea what you're talking about.
Okay, we are calculating shear in this beam.
I knew that.
Shear is just, what are the units of shear? What are the units of shear? Pounds, it's a force. Okay? What is the definition of force? Direction and magnitude. Okay? So, in order to calculate shear in a beam, you just need to figure out in which direction is the force acting. That's all. So we calculated that with 30 and 10 in the middle, you're going to have 25 and 15 as the reaction.
You just start at the beginning.
Yeah, I'll start at the beginning. So, are you clear with me so far? 25, 30, 10, 15?
I see that there are the numbers in pounds up there. Or millions.
Right. Those are my reactions. Everybody knows how to do this stuff.
Yeah.
Yeah? Okay.
I don't know where that graphs.
All I'm doing is I'm basically plotting the shear in the... I'm trying to understand how does the shear force happen in my structure. Okay? So, shear is defined as a force. Force is defined as magnitude and direction. So if I start from the left to the right, how much is the force at say reaction at say this point? Let's call it A, let's call it B, let's call it C, let's call it D. Okay? How much is my force at A? Hey, shh. 25. What direction is it going in? Up. So I'm gonna set a baseline of 0, and I'm gonna say at A it's 25 going up. Okay? Then I move say 1 meter to my right, or even a centimeter, whatever. I just move slightly to my right. How much is the force out here? You don't know. And fair enough. Shear is only a force, right? And remember how we defined shear? It's like one force acting against the other force. Right now, there's only one force that's going up. So it's 25 is constant 25 shear force that's acting along the beam until I hit the 30. Because 30 is going in the other direction. So then it pushes back down with 30 and it gets me, hey guys, you better pay attention on this because we will never repeat this stuff again.
But at 2.1 meters, would it go back up to 25?
Are there any other forces that are impacting it?
You said that it was at 25 right up until
Another force acts on it, yes.
and then it stays at that force?
Exactly, because basically 30 cancelled out 25 by -5. It pushed it back down. So out here it goes like this. Then it gets hit. Hey, you please pay attention to this stuff. This is really important stuff. Because you're going to be doing shear force diagrams all through like structures too.
So you always figure them out by doing the graph?
Huh?
You
No.
always figure them out by doing that graph?
No. I'm just doing a graph so it's easy for you guys to understand.
So then it goes down.
It works.
Oh, you can solve shear by doing a graph. You don't need to do math to do shear. Shear is the easiest thing in the world to solve.
I like that.
Exactly.
I understand. I couldn't hear back then.
Okay, hey guys, pay attention. Hey,
Bananas.
okay, seriously, pay attention because I'm going to tell you the check to know you're right on shear calculation. So out here, it went down by 30. It went down. Hey, Andy, seriously, because you may get it, but I want to be sure others get it. So out here it went by 30, so it went -5. Okay, so this is -5. And then when it reaches point C, another force of 10 is acting down. So it becomes -15. Right? And then it goes up to my reaction. And guess what? The reaction pushes it back up by a total force of 15, which means it goes down to 0.
Should it always be 0, or
The total thing will always be 0.
so it'll always come back to the original
Yes.
0 line?
Absolutely. Okay? Why don't you draw another shear force diagram? Let's do another example. So 16.7.
So what about the x's?
So basically the question is, calculate shear at that point. So the x here, they wanted you to calculate how much shear was at this point. And how much shear would be at that point? -15 inside. So we're going to do,
I like these ones better.
yeah, shear is easy. Shear is really easy.
We just have a quiz on this.
You'll have a quiz on this and moments, so,
I meant like
Just this.
Well,
Yeah, you know?
remember, I've lost a good 1.5 hours on that truss thing because I was like maybe half an hour on the truss and then we move on to
at
this.
least we understood this one really fast.
However, the good thing about this is everything's getting recorded. You are encouraged to go back and review this stuff for something that you don't get.
Dump
It's on YouTube. It's like streaming live right now.
Oh, Andy's on YouTube.
I could go viral.
Yeah, it's like totally streaming live.
Colin teaches structures. Sonny, you should know this, and then you teach us. We'll pay attention.
And if we don't like what you're saying, we'll throw bananas at you.
Oh, no.
Come on. Okay. My class is not over. No.
Yeah, Dodge.
Okay. You can still come talk to Ben. That's okay. Hey, let's do another problem, okay? Elise can solve this one for us.
Oh my god, we had roads.
Yeah, you probably understand it more.
I can explain shear to you in like seconds.
What is it?
Okay, so the problem is,
I don't think so.
that's A. This is 51 kilonewtons going down. At least you like this because everything's in metric units.
Yeah, I love it.
There's 70 kilonewtons going down. Have you found this problem in your book?
Nope.
It's figure 16.7.
Now it's actual.
Especially for my Thanksgiving joke, my yearly Thanksgiving joke. You get it. You get it.
I'll understand without
What?
it. It would be negative.
What is this?
Not actually.
Okay. So the question that you have, hey guys, the question is, again, guys, pay attention because you'll get this in your quiz and you'll be like, it made perfect sense in class and it makes no sense when you're looking at the quiz.
Yeah, it's like trusses. Makes perfect sense in class.
So, how much is the shear at D? Just quickly tell me. So Noah, let's start with you. How much are my reactions?
It's 69 and 52.
Okay, so my reactions are 69 and 52.
I was just trying to finish on
Oh, it's in that.
Okay. Now, the most important thing with shear is you start calculating from the left, moving to the right, okay? So, at A, what is the force that's acting at A of reaction of 69? What direction is it acting in? Going up. So we draw it up, 69, going like this. And then we start moving to the right. Because so remember I told you the shear is maximum where the beam meets the support, right? Because it's just trying to slice down. So out here, it's going with 69 and it starts going steady at 69. Right? Because there's no other loads acting. It reaches point B where it suddenly gets hit by a force of 51 kilonewtons. Okay? 51 kilonewtons, which direction is it acting in? Down. So it goes down by 51. So how much is 69 minus 51? It's 18, right? 18. 18. That gorilla costume has like affected your hearing.
Yeah.
You're like, now you hear like ultrasonic sounds and all, but okay, so this is 18. Okay? Then we start going towards C. What happens at C? There's further force of 70 going down, which means it takes it down to how much? 52.
Is it negative 52?
Yeah. Because, you know, it's the, remember, force has magnitude and direction. Okay. Berta, how much is the question is, how much is my shear force at point B? Exactly. This is negative 52. And how do you know your answer is right? Because when you go to the do the reaction at D, it goes back up to 0. And that's all that is there in shear. At least, did you get it?
Yes.
Shear is the simplest thing in the world to do. Now, okay, guys, hey. Supposing I were designing a beam. Okay? I'm designing a beam. I'm actually designing this beam. And I open my book of sections, like whatever, say I'm designing a timber beam. What section would I choose?
What?
If I were to open a book of timber beams, right? Because the manufacturer will supply you all these like typical sections saying that's the shear force each section can take. Which section would I choose? What's the number that I'm designing for? Maximum number. Remember, the shear is always lowest at the middle of the beam.
Oh, so you just designed for the maximum number across.
Right.
Okay. Like positive or negative. So if the number, if those two numbers were switched, say it went up 52 and then.
Yeah, it doesn't matter.
Okay, so either positive or negative,
Yeah.
whatever.
Because it's basically the slicing action, either it's like slicing it down or it's slicing it up.
Why wouldn't it be 70? If it was a maximum.
Okay, what's happening where it's 70 is it's actually being counteracted.
It's going down.
It was going up, but then it started going down.
So once you got over to 70, it was already plus 18.
Right.
So to go to subtract that 70, it's only going to make it negative 50.
Exactly.
So it's the distance from the 0.
Exactly.
The maximum from the 0.
And shear is always maximum at the point of support. Always. Okay? Good. Now, hey. Slow down. What's the hurry?
I have to brush my face and vitamin C to try and be constantly all day.
I'm driving a car that weighs 1,800 pounds and it's supposed to get to be freezing right.
Huh? What?
Is it really supposed to be raining?
Yeah.
Is it raining?
What?
It's not raining.
It's snowing.
Really? Let me have a look.
Borderline.
With a car that weighs less than a ton.
Well, my car's gonna do well.
Yeah.
I feel like we should be on our side.
Field trip. Like, wishful thinking all the way around.
It's dry, but it's still snowing.
Okay, guys, hey. We need to, now, shear force is easy, right? We do need to study bending moment diagrams. Bending moment diagrams is the last big thing for this semester. And you have to understand bending moment diagrams. There's no two ways around it. Okay? I can do a couple of things. I'll give you the options. The first option is I just continue this class for another hour and a half, and I finish up bending moment diagrams, and we're done. I'm not joking. Remember, I woke up at 6 in the morning and I drove up from Boston.
I didn't know that.
Khalif knows that. And I haven't even had a lunch break today. So I've just been like working nonstop. Anyway, so, I won't have sympathy if somebody's like, well, I've been like at school
You
since
had
9.
3 hours to get some food on your way to me, so.
No, then I would have made it for class. Okay. The other is we have a class on Thursday, and hear me out. I will record the class. In case you can't make it, you can refer to the recording.
That sounds good.
Sounds good?
Recording it on your own, because I don't think any of us are good.
I would strongly urge you, however, make it, because bending moment diagram is important.
Remember that thing called Studio? You know how it's getting towards the end of the year? Yeah, none of us are coming.
Well,
So you can record it.
see, but then the problem is you can get homework and you'll get stuck doing homework.
Yep.
Because I'm using class time to explain homework, we have to come back to class time. Because normally homework is supposed to be explained like on Tuesdays and Wednesdays when I'm, you come talk to me and say, listen, I don't get this. However, that's fine. I realize structures is happening for the first time, and I do realize there's a lot of catching up to do. I don't have a problem with it, but it is critical that bending moment diagram be understood. For the quiz, I will give a simple bending moment diagram question, that's directly related to the stuff we're going to do in the class video. Okay, I'll make that much allowance.
Will it actually be up like that
Yeah.
day?
It'll be up before.
Class on Thursday.
Wait, what?
It's a Blackboard quiz.
No. Will the video be up
Oh,
like on Thursday, or is it gonna be like one of those things where it's not?
Video will be up Thursday because I'm doing it from 1 to 3 anyway. Okay?
When are we meeting? Okay.
1 to, I'll be here at 1.
Right, I'm not meeting for structure, so I'm meeting for studio.
And you didn't say you would help her.
Oh, oh, you have time to sit and work with me on Rhino, but not
For
structure.
studio, yes.
I am so hurt. We can do it after history.
No, I'm not staying after.
I just don't have time before that.
Okay, I'll come to one something then.
You can talk to the person who teaches Rhino. He may be able to work
Who
with you.
is the person? Are you in that class? No.
1 to 3 on Thursday.
1 to 3 on Thursday.
So if you go to the class on